So I would like to talk about perturbation, not perturbation, WKB approximation today, and it will be like first one part, whatever I can do within like I think 10-15 minutes maybe, or maybe 20 at most. I will do. Then the remaining I will do some other day. So what is WKB approximation? It is just a way to solve differential equation, the Schrodinger equation. Uh, if you have complicated potentials and you can't find the solution, then you can use this, provided that the potential is uh, changing very slowly. There are other conditions as well, but this is all I know right now. Some wavelength condition and blah blah blah. Okay, before going that, this is also called a semi-classical theory, and now the idea is, first of all, let's come to classical mechanics first. Suppose I have a potential like this, some potential. This is a value of the potential at any x, and this is the position in 1D. And let's say I have some energy, total energy. This is the total energy. So the thing is, if this is the total energy, uh, my particle can never come in this side, of course. He will only be constrained here. And whatever it is, I know for sure that at any instant this much will be potential energy of the particle, and this much will be kinetic energy of the particle, right? So you can see as it comes closer to the turning point, this point, the kinetic energy will keep getting lesser and lesser. Potential energy dominates, and yeah, here so you can see everywhere, like here kinetic energy is more, here it is greater and greater. Kinetic energy is nothing more but just the length of this is a kinetic energy. And okay, there is a problem, not this is not the kinetic energy, sorry, this is the kinetic energy and this is the potential energy. Yeah, so wait, this is very confusing. What is, so when it is here it is okay, things get very weird. So this is still the total energy E. In this total energy, this much is the potential energy. Okay, things really get weirder. Okay, this is still how it is. So this is the kinetic energy total, and this is a potential energy here. You just subtract this by this and you again get back total. So yeah, basically this curve is there, right? From this curve up to this bar, you just measure the height, that is your kinetic energy, the height. So this is how it looks like here. And the thing is, if you think, assume you have some object, as a tiny object, it's it is tiny in such a way that it is neither too small to be too quantum, nor it is too big to be too classical. Weird, right? Yep, that's how it is. So what we will do is, we will treat this particle in a way quantum, as a quantum particle. If the particle is kind of quantum, then we know that it will have some kind of wavelength, some kind of spread, and you can calculate the wavelength if you know the momentum of the particle. So somehow you know the momentum of the particle, so it's classical, but it has a wavelength. This is quantum. It is so weird, so weird. It's like, what the hell is happening? But it is how it is. So if you write the Hamiltonian of this, like if you know the total energy and all that, you know that this will be at every instant. So let me write it. Momentum square by 2m plus kinetic energy, potential energy, and momentum at every instant, it will be this much, right? And if this is the momentum at every instant, then lambda at any position, so this is momentum at any position, then if I follow this equation, I will simply get what would I get, h divided by square root of 2m e minus minus v of x. This is what I get. So in a sense, or you can just say that this is just nothing but so this will give you kinetic energy, right? H by square root of 2m kinetic energy. I am using T for kinetic energy. So this is how it is. And so yes, the more the kinetic energy, lesser will be the wavelength, right? This is what you can see. More the kinetic energy, lesser will be the wavelength, and so forth. Now the thing is, if the particle isn't not changing its kinetic energy much, I mean, so suppose that as time passes, okay, let me just stay with position. As it's going closer to somewhere it's, as it's traveling, if it is not changing its kinetic energy much, if this is the case, then wavelength wouldn't change much either, right? Wavelength will also be still the same. Sorry, not this wavelength would also not change much, because kinetic energy is not changing much. If these two assumptions if I keep, what all I can do, we will see with it. So first of all, now we will apply quantum mechanics. So suppose I have the same potential now, but maybe I haven't drawn this well, but this potential is changing, but it's pretty flat. I haven't shown it yet. It is kind of flat. It's like a decay potential, you can think. Very very slowly it's varying. That is very important for WKB. And so now if I have the Schrodinger equation, so that I want to study the quantum behavior of this, I don't know, this method kind of, it's like a mixture of quantum and classical. It's like so weird. You know the quantum behavior, you find classical, you know the classical behavior, find quantum. From one to other, you're so you're just intermingling one another. So here it is, right? This is how we will write. So out of nowhere, these people are like, boom, take this, assume that your solution is this, assume that the solution of your Schrodinger equation is this, okay? And you might be thinking, wait, why is this lesser than 1, what is happening and all that, and they have made it as general as possible. So basically u of x is a complex number. So this, if it is a complex number, this overall function can be greater than 1, lesser than 1. It can oscillate, it can do all kinds of things, because of this is I don't know, this is crazy. Since this is allowed to be complex, this function can do a lot of stuff. It's kind of like, I don't know, basically it feels like some kind of uh, how should I say, you have a oscillation and you have this oscillation modulated by some function. I don't know if I'm drawing it right, but something like, I don't know, something like this, some kind of modulation is there. So yeah, I want to draw modulation. I don't know how it looks, but maybe it looks something like this, I don't know. So if this is the case, let me apply this solution here and see what happens. So if you do the math, this is what you are supposed to be getting. I have done the math, so I will just proceed. And I get so this is what we will get, right? This is what we would get. So you can just do the calculations, and now I just cancel this up, and at the end you get something like this. This is just the mathematics, there is nothing physics involved yet. So suppose that I want to find the behavior of this of a particle which just when it is close to the turning point, I want to find out. When it's near the turning point, I want to find out what happens. Maybe it's close or not, I don't know, but it has energy to travel. It is like in a classically free region where it can just it has an oscillatory solution, something like that. So if that's the case, let me say that this function is k of x. So this function, let me say this is k of x whole square. Okay, so now this is my differential equation for the u of x in that e power I u of x. Where you of course know the value, so follow me. So if this is the case, then what they do is uh, since in uh, yeah, that's all they do well. And now then what they say is, since potential is changing very slowly, is it possible that your wave function is also changing pretty slowly? Is it? uh, for some reason they just ignore this term. They just say let's remove this and see what happens and play around. I don't want to talk about it because I myself I know what the final solution looks like, what the final form looks like, but I don't want to talk about it because it might be no point. It will feel dead blank. So this is all I can say so far, and so much of stuff happens. This is the main equation right now, and what should I say? That's it for now. Thank you. Bye.